You must have seen someone throwing a stone up in the sky at an angle. Or sometimes you might have yourself thrown a stone up the sky. But have you noticed something? If you watch carefully, you would notice that whenever we throw a stone or any object up, it falls down due to gravity, but it follows a particular type of path, which is called a parabolic path. In this case, the curve or the path looks like a parabola. We may find different types of curves like circle, ellipse, and hyperbola in various other situations. Each of these curves is called conic section. What does it mean by conic section? In mathematics, a conic section is a curve obtained by intersecting a right circular conical surface with a plane. The intersection of a right circular cone and a plane generates one of a group of plane curves, including the circle, ellipse, hyperbola, and parabola. These curves were studied by the ancient Greeks and were written about extensively by both Euclid and Apollonius. For most of the people, the word cone creates an image of a solid figure with a round base and a pointed top. Let's imagine a vertical line and a second line intersecting it at some angle. That's called phi. The vertical line is called the axis, and the second line is called the generator. The angle between them is called the semi-vertical angle. Now, let's imagine grasping the axis between the thumb and the forefinger on either side of its point of intersection with the generator and rotating it. The generator sweeps out a surface as shown in the diagram. It is this surface which we call a cone. We can observe that a cone has an upper half and a lower half, called the naps, and these are joined at a single point called the vertex. We may notice that the naps extend indefinitely far both upwards and downwards. A cone is thus completely determined by its vertex angle. By intersecting a plane with a cone, we have three choices. Depending on the angle that the plane makes to the vertical axis of the cone, we get three types of curves. First, we may choose one plane to have an angle greater than semi-vertical angle that does the generator of the cone, in which case the plane must cut right through one of the naps. This results in a closed curve called an ellipse. Other plane may have exactly the same angle to the vertical axis as the generator of the cone so that it is parallel to the side of the cone. The resulting open curve is called the parabola. Finally, the plane may have a smaller angle to the vertical axis. That is, the plane is steeper than the generator. In this case, the plane will cut both naps of the cone. The resulting curve is called a hyperbola and has two disjoint branches. We may notice that if the plane is actually perpendicular to the axis, that is, it is horizontal, then we get a circle, showing that a circle is really a special kind of ellipse. The conic sections were named and studied as long ago as 200 BC when Apollonius of Perga undertook a systematic study of their properties. So now we know that there are three types of conics: the ellipse, including circles, parabola, and hyperbola. What about a circle? It is interesting to know that a circle is really a special kind of ellipse. If the plane is actually perpendicular to the axis, that is, it is horizontal, then we get a circle. As described by Apollonius, the circle can be considered as a fourth type of conics, or as a kind of ellipse. The circle and the ellipse arise when the intersection of cone and the plane is a closed curve. The four conic sections can be easily visualized by slicing. We may consider the conic parameters in the case of an ellipse to explain it in details. Conic sections are the curves which are the path of the moving point or locus, whose distance to a fixed point f equals e times its distance from the line L. F is called the focus, L the directrix, and E the eccentricity. The linear eccentricity, that is C, is the distance between the center and the focus or any of the two foci. The latus rectum, that is 2L, is the chord parallel to the directrix and passing through the focus or one of the two foci. The semi-latus rectum is half the latus rectum. Various parameters are associated with a conic section. Circle, x square plus y square is equal to a square. Ellipse, x square upon a square plus y square upon b square is equal to 1. Parabola, y square is equal to 4ax. Hyperbola, x square upon a square minus y square upon b square is equal to 1. Various parameters associated with a conic section are: conic section, circle, equation x square plus y square is equal to a square, eccentricity 0, linear eccentricity 0, semilatus rectum A, focal parameter infinity, ellipse, equation x square upon a square plus y square upon b square equal to 1, eccentricity under root 1 minus b square upon a square, linear eccentricity under root a square minus b square, semilatus rectum b square upon a, focal parameter b square upon under root a square minus b square, parabola, equation y square is equal to 4ax, eccentricity 1, linear eccentricity a, semilatus rectum 2a, focal parameter 2a, hyperbola, equation x square upon a square minus y square upon b square equal to 1, eccentricity under root 1 plus b square upon a square, linear eccentricity under root a square plus b square, semilatus rectum b square upon a, focal parameter b square upon under root a square plus b square. The corresponding conic section consists of the locus of all points whose distance to F equals E times their distance to L. For 0 less than E less than 1, we obtain an ellipse. For E is equal to 1, a parabola. And for E greater than 1, a hyperbola. After studying the conic section in detail, we start thinking about their real applications. Here are some real-life applications and occurrences of conic sections. 1. The paths of the planets around the Sun are ellipses with the Sun at one focus. 2. Parabolic mirrors are used to converge light beams at the focus of the parabola. 3. Solar ovens use parabolic mirrors to converge light beams to use for heating. 4. The parabola is used in the design of car headlights and in spotlights because it aids in concentrating the light beam. 5. The trajectory of objects thrown or shot near the Earth's surface follow a parabolic path. 7. Hyperbolic as well as parabolic systems of telescopes. There are many other examples of the curves called conic sections in nature. we may discuss specifically in each curve of the conic section. Let us look into some specific applications of ellipse. The ellipse has many applications. Elliptical gears are often used for machine tools. And ellipses are used in optics, in telescopes and microscopes. Other examples are orbit of a planet with the sun as a focus, orbits of moons, satellites, and comets. The orbits of the planets are ellipses, and the orbits of moons, satellites, and comets. Next, we may look into some specific applications of hyperbola. For example, comet path, gear design, navigation, and telescopic lenses. The parabola is an interesting mathematical curve. For example, antenna of a radio telescope, cable of a suspension bridge, flashlights, parabolic reflector, and solar furnace. The parabola is the form taken by the path of any object thrown in the air and is the mathematical curve used by engineers in designing some suspension bridges. The properties of the parabola make it the ideal shape for the reflector of an automobile headlight. In an automobile headlight, the light from a bulb at the focus point of the metal back of the headlight reflects and is sent outward to light our way in the dark. The simplest and the most common curve around us is the circle. The circle as a wheel is one of the greatest inventions of all time and the basis of much of our transportation system. Really, it's quite interesting and amazing to know regarding the real applications of conic section and in general the application of mathematics. We must take interest in our life to give a real meaning to the study of mathematics. This would create interest to study further and find new areas of study in mathematics. After viewing this program, you may try to answer these questions. 1. Write the equations for the circle, ellipse, parabola, and hyperbola. 2nd, who is the person who came up with the names ellipse, parabola, and hyperbola? 3rd, who is credited with discovering conic sections and when did he live? 4. Name one real-life application for each: circle, ellipse, parabola, and hyperbola.